Thank you, Kevin, for nice introduction and good afternoon, everyone. Thank you for having me back. It's truly a pleasure to be here, even though it's virtual. So this is really a special occasion for me. I received, yeah, as Kevin said, my PhD training almost 30 years ago. Yeah. So coming back, bring back a lot of fond memories and yeah, especially Dr. Fleming, who shaped the way I do research. I greatly appreciate that. And so it's also a reminder that time flies, and I have been at MD Anderson for 30 years. So that's my first job and still first job. So, but some statistical problems never really go away. Sometimes they just get new names, especially in this era of machine learning and AI. So today I would like to share some of the work based on still the fundamental training and knowledge I learned um, from UW about survival analysis. But with this new idea of the machine learning algorithm, I'm really looking forward to the discussion. So, okay, here's the title. Um, and so the talk will focus on this distribution-free conformal prediction. I don't know how many people in audience are familiar with this concept. But I assume some of you know, but maybe some of you are not that familiar. So I will use maybe the first 10 minutes or so just give some introduction about this concept. In fact, I myself have learned this concept for a few months on and off, and I try to digest what's this conformal inference means and the conformal predictive interval is. The talk is based on our recent paper published in Biometrics June last year. So, well, currently, for most of my methodology work, we do have clinical motivation. As I said, I have been MD Anderson for 30 years, so doing a lot of collaboration with oncologists. I work with a lot of oncologists in breast cancer and also urology. So in cancer research, it's always important to predict the survival outcomes and given patients' risk factor and treatment, so on and so forth. In the example data I will describe today is a small subgroup in breast cancer called inflammatory breast cancer. So this is very rare breast cancer, but it's very, very aggressive. The overall survival for this group of patients are not good. So we have this relatively large data from National Cancer Database. We use that. We have information for individual patients, baseline characteristic, tumor characteristic, and subtypes, and treatment they received. So also they observed time to death for those patients. So in fact, if we can predict survival time directly, really help clinicians and patients to have a straightforward, more like intuitive concept compared to if you tell patients what's a hazard ratio or even median, sometimes they try to digest what that means. So direct to predict the survival time and with uncertainty could be a very important information. So that's sort of the focus of this work. So in fact, over the last 20 years, and most of my research or even collaborative research mainly focused on association study. So mainly like given those observed data, covariates and outcomes, and we try to build a model to explore the association between those baseline covariates or treatment with survival time. But prediction is a different topic. Like, so, for example, like we have a population of interest, it's IBC patients, and we have a random sample of cohort of data, and we observe both covariates X as well as outcome. And we're not directly interested in building models to associate X to Y, but more importantly, we want to predict a future patient. So a future patient coming and she's, let's say, 55 years old and with all those tumor characteristics, we're interested to predict her survival time. So that's the purpose of this prediction. Okay, so the predictive interval on survival time, and of course, we statistician, we acknowledge uncertainty. we can never give like a single predictive value that, oh, this patient her survival time will be 5 years. Well, we don't have that confidence. Usually we would give a range that, okay, maybe 3 to 7 years with 90% of probability. So that's our purpose. So we want to predict this type of interval. And as we know that, given those kind of prediction, it will help us to guide the treatment selection. Listed, this interval will give us the best and worst scenario, so a range. It's particularly useful in heterogeneous cancer. Nowadays, we even call breast cancer is such a heterogeneous cancer because it consists of so many different subtypes and they all have very different prognosis. So the observed data can be complex, and how do we have confidence to assume the regression model or association model is correctly specified? So we all are very familiar with confidence interval. So why do we need a conformal predictor interval? So here is a brief description for some of the difference. So when we estimate traditional, conventional confidence interval or even predictive interval, we need a regression model, a correct model assumption. So this model could be a parametric model. If this model is misspecified, the coverage will be way off typically. So, but yeah, a confidence interval, usually we estimate confidence interval for a particular parameter of interest or like a median, and so on and so forth. Conditional, those typically conditional on covariates X. So we do not consider the variability of X, we condition on X. Or even one step further in predictive interval in the conventional approach, we consider uncertainty of X, jointly model X and T, then construct the predictive interval of T. So there are some work in this area almost 20 years ago by Lawless. But all those works need this correct model specification. So the regression model need to be correctly specified. And for this predictive model, also the residual, the error distribution need to be correctly specified. One unique aspect for conformal approach is that we don't have to have correct regression model specification. We just treat this model, regression model, which associates outcome variable with covariates X as a working model. In the meanwhile, we can ensure the prediction interval has a correct average coverage probability. So we can achieve that for a new patient given with X sub n plus 1. We can estimate the uncertainty range for her survival time, for example, with a probability of 90%, for example. And here we needed to consider the joint distribution of T and S. So just to use this table to summarize what I just described briefly in the previous page. So we're all very familiar with confidence interval, typically estimate unknown parameter, but we do need the correct model specification. And even for conventional predictive interval, with similar goal to estimate uncertainty for a future patient, we need a correct regression model as well as residual distribution assumption. But for conformal predictive interval, with the goal to estimate uncertainty for future observation, we only need assumption of exchangeability. We do not need this strong model assumption, but we do need the assumption that training data and the test data, they are exchangeable. So this exchangeability assumption even weaker than IID assumption. So why? Of course, there's no free lunch, and given this flexibility, typically the estimated conformal predicted interval will be wider than conditional those interval, but they do have flexibility for model free. Okay, so the conformal prediction really we have to give credit to Bob. His 2009 paper really introduced this very fundamental concept of non-parametric conformal prediction, which has attracted substantial attention only in recent years in statistical literature, mainly with those novel machine learning algorithm. With nowadays computer power, I think make this type of method more feasible. So, and Lay and others and propose so bring this whole idea of machine learning algorithm to statistical literature, and so indeed this conformal inference guarantee this overall, we also call the marginal coverage probability, and to ensure this, why we don't have to assume a correct regression model. And the probability is taking over the joint distribution of X and T. So in conventional confidence interval or association analysis, we typically condition on X. We don't really model those variability of X. And the key idea is really we take another layer of expectation to integrate out the distribution of X so that we ensure the marginal coverage probability of this predictive interval. So again, let's rephrase this key idea again. Those are still just Lay's and other people's work about conformal inference. For each patient, you can get the individualized estimated interval given patient their own profile baseline characteristic. On the other hand, this coverage for this predicted interval is guaranteed on average across patients. So the advantage is that regardless of whether the working model is correct or not, the overall coverage probability of conformal intervals remain at a specified level asymptotically. But, well, maybe you have a question that if the working model really, really good, really close to the truth, do we have any benefit? indeed, so working model can affect the sharpness of this estimated interval. So a better model we will have a narrow predictor interval. Otherwise, we will have wider interval. But they are all valid. So they all achieve 90% or 95% coverage probability. So based on the conformal approach. So that's the beauty of the conformal inference. So, and again, we only need to assume data. They're exchangeable between training data and test point. So that's a theoretical guarantee for the coverage probability. Okay, so before introduced to the sensor, the survival data, we just get some intuitive interpretation for conformal inference in a simple setting. So if we just have uncensored data, and typically we will fit a linear regression model. So we have a whole training data set, X, Y. Then in conformal inference, we need to introduce the concept of conformity score, or sometimes we call conformal score, in which measure how well the sample matches the model. The model, remember, it's a working model. It may not fit linear regression, but we just use linear regression for simplicity as working model. Then we measure this absolute residual between the observed and the expected or predicted from the training. And then based on the conformity score generated from the training data set, we just rank them. It's just a rank-based analysis. Then we were trying to find the cutoff of the two quantile, lower quantile, 1 minus like 5% and up 95% quantile. And then invert those score to find the conformity interval for the outcome of interest. Here, I just want to quickly touch on this concept of marginal coverage. We ensure the marginal coverage of this predictive interval. It's not conditional coverage. What the marginal coverage means that maybe some covariance regions for those estimated predictor interval may be overcovered and other undercovered, but overall the average is correct. So now let's move to the sensor the data part. Remember that exchangeability between training data and the testing data, that's a key assumption. But in survival data, in fact, this exchangeability violated. The reason is that for sensor data, the observed training data, we have some people, we only observe their sensor time, not failure time. Then this, the new test data, we really want to predict her death time. We're not interested to predict her minimum of death or censoring time. So basically, the observed training data and testing data, they're not exchangeable anymore. So we need to do something to somehow regenerate those exchangeable data. So another thing is, remember, we need to estimate a conformal score for censored observation. Like in this simple example, we don't have observed failure time. We only have a sensor time. Then such measurement of residual doesn't make any sense. So not very meaningful. Well, 2 years ago, Candy's group developed this extend the conformal inference to right sensor data. It's a very important paper published in JRSSB 2023. So in order to deal with right sensor data, they did a lot of interesting things like truncated data uh, uh, to select a portion of subject in the right censored group, and with their censoring time greater than this truncation time, the choice of this truncation time is a bit ad hoc, and then even worse is that they can only handle type 1 censoring. So compared to general censoring, type 1 censoring means that we know everyone's censoring time. Even though this patient died at year 3, we pretend we knew her censoring time. So typically in medical research, that's impossible. And maybe in industrial reliability, those study to test the reliability of TV or some device, we can set up regardless when those machines fail, we just follow them for 1 year, let's say, put it that way. So then in that case, we know everyone's censoring time. And so even under those restrictions, they can only construct a lower bound for the minimum of the death time and this C naught. So it's quite complicated. They even constructed the covert shift for this subcohort and try to construct this lower bound. Unfortunately, the methodology cannot be used for generalized censoring and can only produce one-sided low bound. So we try to handle this data from a different perspective. We propose a bootstrap-based conformal inference use resampling approach. We want to deal with general right sensor data. And we also like to estimate a two-sided predicted interval rather than a lower bound. Even though lower bound is informative, but not as informative as a two-sided interval. In the example later, I'll show you. So for survival data, we use this conformal score based on survival distribution. We will show later that why this is a very robust and natural choice. For survival data, it's a bit hard to use residual, but some people use the difference between survival probability minus 0.5. So use median as a reference point. Okay, so one key step in our approach is remember that the observed training data and testing data are not exchangeable due to the right censoring. So we consider the joint distribution. Also in conformal inference, we're dealing with joint distribution of T and X rather than conditional X to model T. So using training data, we estimate the empirical distribution function. This is a non-parametric distribution of T and X. So this seems to be very natural to propose this and just use the inverse weight for the censoring times to adjust the censoring. So this joint distribution of T and X, in fact, just reduced to Kaplan-Meier estimate if we integrate out X. So for marginal distribution of T. So why we want to construct this empirical distribution of F hat? We using training data, even though they are right censored, we can still consistently estimate this joint distribution. Then we will use this joint distribution to sample uncensored data from there. So in that case, we can use that data to construct conformity score. So that's our idea. So, and this way we also accounting for all data variability, the joint both T and X. So then the next step, well, we need a working model. So working regression model just associate covariates X and outcome T. So you can use any parametric or semi-parametric models. Just for sake of illustration, people are all love Cox model, so we just use Cox model to illustrate the approach. And we assume our working model to associate outcome with X and as usual Cox model. And we denote the covariate coefficient beta and baseline hazard, all those unknown parameters as a theta. So then use the training data. We have training data like from NCDB. The training data consists of the minimum of desk time and censoring time and the censoring indicator and the covariates. Then we use that just as our usual practice, estimate the unknown parameters theta hat. So now our purpose, remember, is that given the new patient's baseline hazard, we want to predict her range of survival T. Okay, here is a step-by-step algorithm. So we use original training data from the last page. We estimate theta hat, and we also estimate this empirical cumulative density function F hat. And then to introduce another layer of some variability, we bootstrap sample from original training data and with equal probability and estimate another set of theta hat star on a working model, same working model. Then we randomly sample one pair of uncensored. Remember that since we sample those pair of failure time and the covariates from the estimated empirical function. So those are uncensored. And then we calculate the conformal score. Conformal score just defined by the survival distribution, survival probability. So then we calibrate that. This two-step is really, the purpose is to calculate conformal score, and then find the lower and up quantile of this conformal score. So we estimate those conformal score, and the beauty to use survival probability to define conformal score is this is a monotone function, and we can just inverse this function and solve the predictive T from that. So even computation-wise, it's very straightforward. So I know that's a lot of things, even though just the 5 steps, 6 steps looks not that complicated. But let me use the next page to illustrate this idea a bit more. So really, we want to use the conformity score to calibrate the boundary, the quantile, the lower half of alpha and up quantile. That's based on conformity score. And then remember those conformity score are calculated based on those bootstrapped sample. Then for the new sample score, and of course, we have x sub n plus 1, but we don't really know what t will be. And so we just insert that to the function and compare to rank the training score. So as long as this fell into this range, then we keep that. So basically, it's just theoretically just to solve this following inequality for t sub n plus 1. So now we can solve that t from this inequality. But remember the R and the L, those are left and the right quantile of 1 minus alpha. So those quantiles are calculated or derived from the training data's conformity score. And then we just, based on that rank conformity score, we can derive the predicted interval for this new patient T, new patient test time, T sub n plus 1, given her baseline covariates. Any questions? I know that's so if you already know conformal inference, maybe that's relatively easy, but otherwise it's a bit dense, the contents. So indeed, and all those, we assume all those training points as well as this test point, they're all exchangeable. So then it's reasonable to assume that new score lands in this range with probability 1 minus alpha. Yes, please, Elizabeth, I saw your hands up.
Yeah, I did have a question on a previous slide.
Okay,
I don't remember how far back you need to go.
okay,
It had an indicator. Here we
yeah,
go. Yeah.
okay.
What does it mean for xi to be less than x? Like x, I'm assuming x is a vector.
Yes, it can be a vector. Yes,
Yeah,
xi
so
can be a
so what
vector.
does it mean for an observed xi to be less than some x? I'm a little bit confused on that.
Okay, so if you consider the very simple case, if x is just the baseline age, and you can estimate this empirical distribution by using this formula. So, but if this x it so this way, even though it looks like it's just like a more like a bivary, but it's multivariate. So x is a vector. It could be continuous or even categorical variable. You can use that to estimate. This is just a non-parametric estimation for the joint distribution. Let's see how to put that way. For the non-parametric, empirical non-parametric distribution. So maybe we have learned from multivariate model, but the new part is really for our constructed, this function is the inverse weight to handle right censoring. If there's no right censoring, those type of non-parametric CDF is very has been in literature for a while.
Okay. I'll have to look it up. It's a little bit
Okay,
confusing to me to think of a vector being smaller than another vector. So,
okay.
okay.
Uh, no problem. Okay, so then we extend this approach further. So remember in this formula, we just showed that here we assume this censoring times independent of covariates. but we can generalize this condition. In case sensory time depends on X, we can model that, but we have to model that consistently. So that's a restriction so that the whole F hat is consistently estimated. That that is required to ensure that this conformal uh, inference work, even though the working model can be flexible. So we can also estimate the conformal predictive interval for remaining lifetime prediction. So in clinic, it's also very common that a follow-up patient uh, comes and she already survived 1 year or 2 year after initial diagnosis, and then what's her future looks like. And so we can predict, given this patient's current survival time, and to predict her additional survival time after initial diagnosis. Um, here, maybe I don't have too much time to describe all the details formula for how do we handle a covariate dependent sensory scenario. But one interesting thing is in simulation, we check how robust, how bad it could be if we ignore this dependence between sensory time and the covariates. So we pretend they're fine. We just use Kaplan-Meier of the sensory time as weight. Um, well, in fact, most of the time they are fairly robust. But when this association between covariates and sensory time is very strong, and that can lead to undercoverage of the predictive interval. Predicting remaining lifetime, we can just modify our conformal score and to incorporate this conditional component, and can derive the remaining lifetime interval similarly. So I'd like to use some time to show some numerical results, hopefully. Okay, so we did a lot of simulation, but just hopefully just the 1 page of simulation here. What we like to demonstrate that is if model is misspecified, and the conditional coverage will do badly as expected. So wouldn't achieve a correct coverage. But the conformal predictive model, they all did very well, and with low and moderate censoring. But I present the worst scenario that we have pretty high censoring, heavy censoring. So 50% censoring. In that case, if we use Cox model as working model, it also lead to under coverage. So if we have heavy censoring, the interesting thing is, regardless how your data are generated, either Weibo or log normal, you need to use a parametric working model to derive this predictive interval. They're doing very well. But I think it's understandable for Cox model, when there is a heavy censoring, the tail behavior is bad. So we can't extrapolate to estimate upper bound reliably. So that's caused the poor performance if we use Cox model as working model when censoring is heavy. So that's the point I like to emphasize. Really, traditional conditional model fails as expected if model is misspecified. But conformal, overall, they're doing great, especially with light censoring. All working model, they do well. And Cox model even generated the narrowest intervals when censoring is not heavy. It's quite robust. But when we encounter heavy censoring, we should not use Cox model. It tend to undercover because at the tail, it's the upper bound estimate is not reliable. Mm. And also, correct walking model wouldn't change coverage significantly, but reduce interval length variation. So if our working model is just the right, correct, we generate the data from Weibull distribution and we use Cox model or Weibull fit that. Well, even log normal, you fit that their coverage is fine, but just wider, they will have wider predictive interval. And also we assess how sensitive to the bootstrap repetitions and we vary those value 500, 1000, 2000, and pretty stable and only slightly decreased standard deviation of the interval length and no impact on overall coverage. Okay, here's the example data. So remember that we are dealing with this IBC patient population. We like to estimate the predictive interval for the survival time, patient-specific survival time. So we have a new patient coming, 55 years old, white woman with IBC, node status N2 and a poorly differentiated tumor. So conventionally, there are those different treatment options for her. She can receive surgery only, or surgery plus chemo, or surgery in combination with radiation, or we call it trimodality. She received chemo first and then surgery, then radiation. So based on the training data, and because it's a rare disease, even among like 30% of US cancer patients, we have about 10,000, and but we remove missing data. We have 4,200 with full data. We have those covariates information, and that's the training data we use. Then remember that we want to estimate the 90% predictive interval for this woman for her survival time. Then in order to do that, we just want to decide what best treatment option for her. So using the training data and insert her own characteristics, that's the estimate predictive interval we obtained. Those four different treatment strategy. Surgery alone, surgery plus chemo, surgery plus radiation, they're similar, and the trimodality. Trimodality looks like the upper bound much higher than other. So we also use the three different working model, and they're not that far, that different. And but since for this data set, censoring is about 50%. And we prefer to use estimate from this two parametric model. Even Cox model, yeah, they have wider confidence interval. So again, those interval, in fact, tells a lot for the clinical insight. One thing is the lower bound, they're not that different. So only about a few months difference, even among different treatment strategy. But really the difference when we compare surgery alone versus trimodality, that's really different. It could be up to like 3 to 4 years different for the upper bound. If I was that patient, I think I would choose trimodality, right? So the minimum, like the worst scenario, they're about same. So that means using that existing method, if we can only estimate the lower bound, it's not that informative. Uh, Really, the hope for long-term survival can be found in upper bound. So upper bound across those different treatment strategy, they vary by even 3 to 4 years. So really, those predictive intervals can help to review treatment benefit beyond like a 1 point estimate. So it's clinically informative. Yeah. Similarly, we can also assume this patient already survived 2 years and uh, in her follow-up uh, checkup, if she initially received trimodality, that's her 90% predictive interval for remaining survival time. And we can see that lower bound are very similar. So key takeaways. Conformal inference really provide a distribution-free prediction intervals for survival time. The working model is flexible. If it's a really good one, it affects the width, the sharpness of the interval estimate, but not validity. It can ensure the coverage. And here, in order to handle generalized censoring, we propose this non-parametric estimate of f hat. And based on this estimate, we can sample uncensored failure time from this f hat. So we sort of avoid directly deal with censored data. So here we can deal with uncensored data. We just resample those data from the estimated f hat. Also, we can estimate the two-side interval, and which apparently can provide more clinical insight than just the lower boundary. And this resampling-based calibration provide a practical alternative. So in most of conformal literature, calibration stage, calibration, and then to estimate the conformal score, mainly based on splitting data set, splitting the training data set. So here we avoid that. We use resampling to achieve the same purpose. And the programming code available in GitHub. So I think I will pause here and thank you all.
Thank you. That was wonderful. Any questions from our audience? I see
Oh,
Marco
Michael.
opened his camera, so I'm imagining he has a
Hi.
question.
I raised my hand too. I didn't just trying to be civil. So hi you. Nice to see you.
You can
Thanks,
fight
thanks for the
to
talk.
speak first.
Yeah, and you hear
Yeah,
me?
we have known each other for a long time, but do
Yes,
those lengthwise the sampling.
exactly. Going back a long, long time. So a few questions I have, or clarifications perhaps in some cases. The first is, so maybe in this case, this doesn't really cause a problem because of survival perhaps is but I guess it really depends. If you're dealing with an aggressive cancer where survival is a bit limited, maybe what I'm about to say is not going to be so much of a problem. But as you know, censoring could preclude the identification of the tail of the distribution. That's why learning means is very difficult in survival analysis, right? Because it depends on the entire tail. And
Mhm.
this would then be a problem here, right? If you cannot learn the entire joint of T and X, if you could only learn it up to a certain T, then
Mhm.
presumably everything else will have issues, right? So are you making an assumption here that censoring does not preclude the identification of the entire distribution?
I don't have to make that assumption. explicitly. But another way to estimate this predictive interval with a more meaningful desk time is we restrict it to the minimum of T and the maximum desk time we observed from the training data. So in that case, so for example, in the training data NCDB, the uh, the longest death time we observed for this IBC population is 10 years. Let's put it that way. We assume that. Then, I can very reliably estimate the predictive interval of this future patient's death time with the minimum of this 10 and T.
Sort of like restricted mean, like
Yeah,
in
yeah,
the
yeah, yeah,
spirit
yeah,
of restricted
exactly.
mean.
Yeah, yeah,
I see.
restricted at the
I
10
see.
years.
Okay, that makes sense. That
Mhm.
makes sense. So you said so I was going to ask you about censoring and independent versus conditionally independent, but you addressed that. But you said, oh, we can use a Cox model there. But you could also use presumably a machine learning based algorithm, right? I mean, to learn the conditional survival function of the censoring time given covariates. But presumably then you would need to change because the estimator you're using for that joint doesn't
Mhm.
seem to be an efficient estimator, right? It's simple. It's very simple to
Simple, yeah,
describe.
not necessarily the most efficient. No, yeah.
Right, right.
Mhm,
And
mhm.
and
You're
so
right.
so
Mhm.
so presumably, I mean, I guess you don't care about interpreting censoring or anything like that. I mean, it's not as if you care about the structure of a regression model for the censoring time. So it's just a nuisance that's part of it. So presumably you could be flexible there as long as you modify the estimator of the joint so that it supports the use of a machine learning algorithm for that nuisance, correct?
Yes, yes, we can. Just the
Okay.
computation wise, maybe nowadays maybe it's all not the issue for
All right.
computation. Yeah, yeah.
And related to all of this is, sorry, stop me, Kevin, if I'm going
No,
too
no.
long, but if you showed plots with different intervals with different lengths, and I was trying to think, okay, what accounts for that length? And tell me if I'm wrong. I would think that the length of the interval or differential length could be due in part to heterogeneity in the spread of the distribution for different groups, but it could also be due to the differential uncertainty for the underlying quantities that are powering this, like conditional survival and so on, right? It could be due to both these things. And so if that's the case, then there would be a benefit to using perhaps the more efficient estimators, right? Because at least it would reduce whatever portion of this length is due to the uncertainty in the underlying estimate of your capital F. Does that make sense?
Yeah, it may make sense. Yes, you're right. Indeed, those predictive interval, they are they take into consideration of all those uncertainties, covariates and the times, so on and so forth. So yeah, sometimes could be wide. However, it's the beauty of that it's honest uncertainty quantification. It's sort of strongest possible guarantee without model assumption.
Great.
Remember that
Awesome.
we don't have to assume model is correct and
Right.
then yeah.
Makes sense. Okay. Thanks so much. Sorry, I asked enough.
Okay,
I'll
you're
let the
welcome.
others ask.
Thank you for your question.
Thank you.
Lourdes.
Thank you, Yushen, for this presentation. Very interesting work. I have two questions, and it's pretty much related to the applications that you showed
Okay.
to us. So you started with a very large sample, but then you had to do actually discard a lot of the data because of missiness. Are you a little bit worried that maybe your sample ended up being so selective that whatever prediction that you're getting may not be really representative of what you would observe for this population?
Yeah, it's possible, totally possible. So if I remember correctly, yes, some of those patients we have to delete is the even their survival time has some issues. And for missing covariates, we're less concerned, but still for the simplicity to just more like illustrate the method.
Okay, got
we
it.
make them, the more like a complete data, yeah.
Okay. And then the second question, it is, are you actually following, for outcomes for this new sample of folks that you're predicting, just to have some validation of your prediction intervals?
Good question. So this is just a assumed example in the setting of prediction. But in fact, in this paper, in our supplement material, we did a lot of more careful in-depth analysis. We even do the cross-validation, do splitting, for the example data. We make sure those estimated predicted interval, they do have good coverage. And then we use in this prediction.
Okay, thank you.
You're welcome. Thank you, Lotus. Next.
Ali?
Ali?
Maybe I'll let Andrea ask because my question is a little bit unrelated. So I'll let Andrea ask first and then I'll go back.
Okay.
Okay, thank you, Ali. My question is about the motivation that you gave us for doing conformal inference. I'm a bit concerned with treatment choice being the motivation, because ultimately what you're doing is relying on the association between observed covariates and treatment to decide. And there's always the issue whether those covariates suffice to control for confounding. And so do you have any comment about that?
Good point. Yes, I totally, yeah. Typically, I know as Tom student, we would like to use gold standard randomized trial to verify treatment, which one is the best, right? But unfortunately, especially for those rare cancer, there was none clinical trials compare those different treatment strategy. We can't really, randomize those patients or to even they have similar tumor biology, tumor characteristic, but we can't say that you're randomized to surgery alone, and another was randomized to trimodality. So it's basically all based on observational cohorts, and we estimate this.
So the assumption is that the covariates that you're using are suffice to control for confounding, basically. There is that underlying assumption.
Not necessary. I guess even when we interpret those predictive intervals, we can sort of say that that's a hypothesis generating, but it's not really causal in any sense.
Right. No, but what I'm saying is that, right, when you are using the intervals, the conformal intervals, to choose to actually recommend treatment, I fear that you are making a causal assertion. I mean, a causal inference assertion. So anyway, so
we need to be cautious, but on the other hand, those uncertainty quantification sort of try to implicitly model observed, unobserved, a lot of uncertainties, in this system. Yeah.
Okay, thank you.
Thank you.
Yeah, maybe we'll take the two last one, Rui and then Ali. I don't know if Ali you wanted to go next.
I'm happy to go sort of either way.
Why don't we take Rui?
Yeah,
Gee.
I mean,
Yeah.
Rui, go ahead, please.
Thank you. Thank you. My question is, like, in your first step, you need to consistently estimate the distribution function. So is that correct? Like, you can replace the estimator with any consistent estimator for your for the distribution function. So you don't, yeah,
So yeah, this one, any consistent, yes. Yeah. If you have other ways to consistently estimate the joint distribution of T and X, then you just sample those data from there. That's fine. Yeah.
I see. So the reason why you don't want to specify a model for the outcome is because you want to do some like model-free inference. But here you still need to specify a model for the sensory, right?
Yeah, yes, that's a limitation. So we're working on some potential double robust method, but that part in order to make sure this conformal predictive interval theoretically proper, and we have to assume this estimate is consistently estimated.
I see. Thank you. Yeah, that's my question.
Okay.
Yeah, so I mean, Andrea asked the first part of what I wanted to ask, but so I asked something slightly different. So this was really interesting in the sense that you're extending conformal inference to the setting where the exchangeability does not hold in the original sense. Do you have thoughts on sort of whether similar strategies would work in other settings that exchangeability does not hold? For example, in longitudinal data setting and things like that?
Very good question. Yes. Yeah, I believe so. Even though we haven't worked on longitudinal data setting. Yeah.
Okay.
But the cautious note is that that part of data regenerating this function need to be consistently estimated. That requirement is needed, even though the working model part is very flexible. So
I mean, the reason I asked about sort of longitudinal data in particular is that sort of in that case you have correlation across observations, and that's what I was wondering, sort of whether this strategy, which is based on Bootstrap, would continue to work in that setting.
Intuitively, I think so. Yeah.
Okay, cool. Thank you. I think Marco might have some follow-ups.
Thank you. Thank you all.
Yeah, no, I just have a quick question again.
Sure. Okay.
Which is because you were just showing the slides. And so when you're estimating the joint of T and X, you're non-parametric. But then you have this working model. And is the motivation for that working model just because your score requires you to have the conditional survival? And you're saying, well, that joint I estimated is not going to give me, well, I mean, of course, it implies everything. One can take it and sort of smooth it out to get a conditional survival from it, that's non-parametric rather than model-based. So does anything stop you from using any flexible machine learning based estimator for the conditional survival function in that step where you compute the scores? Or do you need that thing to be sort of a root n consistent quantity, consistent estimator, sorry.
Okay. Apparently your question has several layers. So I try to let's go back. So
I guess the conformal score there. You see that is
conformal
based on the
score,
conditional survival.
Yeah, conformal score is sort of different from the initial, like the way this part of the consistent estimate for this part is in order to later sample sample those uncensored pair of data and to calibrate the conformal score.
Mm-hmm.
Yeah. So the conformal, using a working model here, the purpose is to derive conformal score. And conformal score can be even defined in different ways, multiple ways. But here we found that using this survival conditional survival function seems to be very easy to use and the monotone function, just invert that and so also very robust. So that step really is to derive the conformal score. The conformal score plays a very interesting role in conformal analysis. Is that this score itself try to really generate a set of score values, and you just rank them, and at the end to find the upper and the low bound quantile for the conformity score, and then invert back to the quantity of your initial interest. Here is to t. So the score itself
So,
based on the scale of probability.
but what happens if that particular working model is heavily misspecified? Like, is there a benefit to having something that is closer to the truth versus further from the truth?
Oh, of course, always close truth is better. You will have narrow predictive interval. At far away from truth, then all those conformity score were split far away, and then this two bound, so the inverted predictive interval will be wide as well. So in order to ensure the coverage probability to maintain at 90%, a bad working model will lead to a wider interval.
And
that
does
makes
anything
sense?
does anything stop you from using, instead of a model-based estimator of the conditional survival function, a non-parametric estimator of the conditional survival function?
No, nothing stop you doing that.
Okay. Okay, great. Thank you.
Thank you. Thank you all for a very interesting, afterwards discussion. It's an amazing group.
Yeah, well, thank you all. That was a lively discussion. And so that I guess concludes our seminar. So let's all thank Dr. Yushen one last time. And if you have any more questions, I'm sure there's a fun email exchange to be had. And hopefully we get to see you in person sometime in the near future.
Okay, thank you. Thank you, Kevin.
Thanks
Thank you
you.
all.
Thank you.
Take care. Bye-bye.
Bye-bye.
Thank you. Bye bye.